All right, good morning. So today in Calc 2, we are going to talk about integration by parts. And integration by parts is one of those topics that is going to plague you for the entire class. So I would urge you to practice this one and to recognize like when you need to work on this. Okay, when you need to use this specific technique. All right. It can be a little tricky because part of the thing you have to do is like you have to decide when to use integration by parts, and you have to decide when you're going to use substitution or another technique. Unfortunately, in this class, there aren't too many extra techniques to learn, which is a problem because most videos you're going to see for Calc 2 assumes the engineering Calc 2. And yeah, there's a lot of techniques that we don't get to because we don't have trig. Okay. So be careful about the videos. There's going to be a lot of times you're going to see stuff like that. And that's the way it is. So let's go ahead and see if we can't do a couple of problems, show you why it works and what we're doing, and then maybe do a couple of homework problems. Okay. Should have timed this. All right, here we go. So let me share my screen. So here is a fresh clean piece of paper here, and let's see if we can't go forward. So you guys remember product rule, right? If I have to take the derivative of uv, right, what was that? It was derivative of the first times the second, plus the first times the derivative of the second. Okay. So I'm going to rearrange this. I'm going to say this is u dv plus v du, right, is equal to the derivative of ub. What my goal is here is I want to take the integral of both sides, but not yet. Okay, we're gonna slide some things around just a little bit first. So what I want to do is I want to go ahead and subtract v du from both sides minus v du. So I have u dv is equal to the derivative of v minus v du. Okay, this is integration by parts. Okay, so when you've got a problem that you have to work with, okay, what we're going to do is we're going to pick a u and a dv, and then we're just going to start solving over here. Now, okay, you have to memorize this. I'm going to show you the problem, and every time I do it, I'm going to do it the same way. So I draw a little box to do things with. Okay, there's another couple of few shortcuts and a couple of things you should remember, but a lot of it is like for the general and wider case. So I want to caution you that a lot of the stuff that people use to memorize this ain't always going to work for you. Okay, so because again, they have more choices, so they have to figure out ways of narrowing them down. All right. So what if I wanted to take the integral of the natural log of x dx? Okay, this is like a v case. It's like, isn't it just 1 over x? Like the derivative, right? The derivative of natural log x, right, is 1 over x. But what's its integral? And it turns out like that's not, you don't know that. Okay. So what we're going to do is we're going to set u to be something, and we're going to set dv to be something. Now, here's the difference. Like when you could use substitution, there was some stuff you could kind of slide around. You could solve for this or that. You could pretty much then meld this to what you needed. With integration by parts, like you got to use up everything in here, okay, in order for it to work. So here we're going to say, well, I can take the derivative of the natural log. We just did that. So why don't we set u to be ln x? And we need whatever's left over here. Well, we used ln x. What about dx? Did we use that yet? No. So that's what I'm saying is like we have to use all the pieces up. Okay. And then the next thing we're going to do is I'm going to take the derivative of this right afterwards. So the derivative of natural log x is 1 over x. And the integral of dv, right, is just going to be x. So you can see it makes a little, right, we have a little box here. And what we're going to do is, here's my UV, okay? So this is x ln x minus, okay? So let me go ahead, right, this was UV minus the integral of v dq. So here is, I'm sorry, of right, minus, and we're going to hit that one. So minus the integral of v du. You got to be kidding me. Is it that easy? Yes, yes it is. Oh, they get harder. Okay, promise. X over x is going to be 1, right? And then we just go ahead and say x ln x is x plus c. And a lot of people write it this way. They say x, and then they'll put parentheses here, ln x minus 1 plus c. And that'll be our integral of natural log x dx. Okay. The most common issue with integration by parts is students don't recognize when to use it. Okay. Well, not anytime. When you have an f of x, g of x, and you're trying to integrate those, okay, you may not, under any circumstances, separate those functions and say, well, that's f of x times integral of g of x. A lot of students like to do this, okay? It is one of the worst things you can do, right? So try really hard. Like if you see two functions that happen to multiply, like try u substitution, right? Try multiplying them out, but try u substitution first. If that doesn't work, then go to integration by parts, okay? So far with the integration techniques you have, things you want to do is you just want to try direct. Okay, always just try direct. I don't know, can I integrate that with the rules I have? Yeah, okay, we're good. Second thing, did I find a u sub? Okay. Again, you may guess the wrong u sub. So you might be on this step for a little bit. You might say, well, what if I try this? Or what if I try that? And then if that fails, I'm like, okay, well, integration by parts. And just where you got the wrong choice here, there are times you're going to get the wrong choice for like what should be u and what should be dv. Okay. Now there is a little trick to remember, like which ones to pick, but you don't. It's not always going to work. Okay, I'm just going to warn you that it's not 100% sure. It's like 80%, 75%. Okay, so 3/4 of the time, this is going to work. Okay, but this is overkill. We are dropping a bowling ball on a fly. All right, this is what we're doing here. And L stands for logarithm. I stands for an inverse function. A stands for algebraic. T stands for trig. And E stands for exponential. Okay, like, the x kind of thing. What do I mean by inverse function? Well, I mean like the inverse tangent. But I don't know that. Like, I know, that's why it's a bowling ball. Okay, algebraic, these are polynomials. Okay, trig, well, we have inverse tangent. How about just regular tangent? Okay, and exponentials. So you're good with this one, you're good with this one, you're good with this one. You don't use any other ones in the class. Like, I'm not going to spring, like, here's an inverse sine on you. We don't do that. Okay, we don't get to do the one integration by parts that causes the rest of the engineering students nightmares. Okay, so you have to do it more than once. It's tricky. You'll get to do some tricky ones too, but like this one is, everybody remembers this when you've done it. And this is like, which one are you picking for a derivative? Okay, we're going to try to pick log for a derivative first, then a polynomial. And I actually would try to pick this one first, unless I can't integrate the other one. So, because polynomial, when you take derivatives of polynomials, they get smaller, right? I take the derivative of like x squared plus 2x plus 7. I take the derivative, right? We get 2x plus 2. It's a smaller function, right? Because the 7 can. If I had to do this more than once, okay, the next derivative is just going to be 2. Okay, so you might be doing this more than once. Okay, so integration by parts. It's great. It's not just a one, you put the key in and unlock it and there it goes. You might have to put the key in, turn it again. In some cases, turn it again, and then you'll start unlocking it. Okay. And the last thing you want to pick for a derivative with exponential, because exponentials are really easy to integrate, right? Like what's the integral e to the x dx? Right? Easiest integral I'd ever ask you. So exponentials kind of want to save, but this doesn't always work. So what I'd recommend, like, try to look for stuff like, can I take the derivative of that, or is it easier to save for the integral? Okay. Logarithms, you can't integrate logarithms. You don't have a nice, easy way to do that. Okay. Exponentials are almost always something you can integrate. Okay. And everything else is kind of a, well, maybe. Okay. But if you're gonna watch other videos on this, you're gonna see this. Okay. And you're gonna look at that and you're gonna say, wait a minute, I've never seen that before. I know, it's for the engineering students, it's not for Calc, it's not for elements of Calc 2. Okay, so you only have L, A, and E. It doesn't make really much of a, right? Lay maybe, I don't know, but it doesn't really make much of an acronym. And yeah, you have to remember 3 things. So when you see that, just realize like that maybe not the best. All right, we've probably had enough of me talking like this. Why don't we make sure we do some more examples so you guys can walk through this. Went through and I said, well, let me go ahead and do your little bit of homework here. We have a polynomial. Okay, this is a very, very common. So we're going to integrate 4x e to the 5x. Okay, so there are certain forms that scream to you, hey, use integration by parts on this. Anytime you have a polynomial of x times an exponential function, that is pretty much, I mean, unless this exponent just happens to, its derivative happens to be that, you're pretty much looking at integration by parts. Okay, so what do I mean by that? If I have an x e to like the x squared, like, hey, if I set u to be x squared, du is equal to 2x. Hey, what do you know? I happen to have a 2x there. Okay, see, like any problem in the substitution section, and there's going to be a lot of these, right? But when this derivative is not equal, okay, that's an integration by parts. Anytime you have a polynomial times a logarithm, this should be screaming at you, hey, do integration by parts here. And again, not all the time, right? I mean, we could do like 1 over x ln x, set u to be ln x, du equals 1 over x, dx, right? And I want to integrate this. So this is integral 1 over x, 1 over ln x. There's a times in here. Okay, sometimes separating them out makes it really easy to see. That's why I do that. And then here's my, right? Let me rewrite it so it's, I've got it sorted out better. Right, that's my u, or my du rather. Here is my u. So we have, this is 1 over u, because it's 1 over natural log du integral, and that's the natural log of u. What was u? U was the natural log of the natural log of x. All right, so it's a very flat function. Okay, so that's another one. It's like, let's just do substitution. Okay, so let's go on to one that you can't do this with, right? So here we go. We have integral of 4x e to the 5x. If I try to take the derivative of the 5x, I just get 5dx. That doesn't help here. Okay, so I tried to use substitution. It didn't work. Let's go ahead and do integration by parts. Okay, so we need a u and a dv. Okay, so of these two, right, f 4x and e to the 5x, which one of these is going to get smaller? Well, the 4x is going to get smaller. Okay, here we have dv. Okay, so du is equal to 4. v is equal to 1/5 e to the 5x. All right. So if you needed like a little u substitution, like a mini, we use u so much. Okay, like I would use something like w or something like that. If you needed to set w to be 5x and then dw was 5dx and do like a mini one here, nobody's going to know. I'm not going to judge you on that. Okay, I'm going to judge you, did you get the right answer? I'm not going to judge you on the intermediate steps. I don't care. So if you needed to do a little tiny one here, what I did is I guessed and then I took the derivative. Okay, but there's my little box, right? I need uv, right? uv, so this is 4x times 1/5 e to the 5x minus integral, okay, 1/5 times e to the 5x times 4dx. Now I'm going to move some things around here, right? So this is going to be 4/5 x e to the 5x minus, I could move this 4/5, right, outside of the integral because they're constants. We have integral of e to the 5x dx. The nice thing is, if you did have to do this, like you needed like a w substitution, you just did this problem. So you don't need to do it again. Okay, so this is going to be 4/5 x e to the 5x. And then integrating e to the 5x, that's minus 4/5 1/5 e to the 5x plus c. So our answer here is 4/5 x e to the 5x minus 4/25 e to the 5x plus c. We could be fancy about this depending on what you want. You know, we could also say this is 4/5 x minus 4/25 plus c e to the negative 5x times e to the 5x. Right, all I did was pull 5x out of each term. I multiply it back in. This goes back to a 0. This goes back here. This goes back here. Everything is good. Okay. So depending on what the format of your problem you need, you might be doing this, but I'm sure, like if I saw you do this on a quiz, I'd be ecstatic. I'd be like, yes, they got it. Okay, life is good. If Math Lab is going to look at this and say, yep, that's the correct answer. I don't know if they're going to take this. Okay, we could try, but I don't know if they will or not. Well, let's see what, we could test it. Okay, so we'll say this is 4/5 x e to the 5x, okay, plus 4, oh, is it plus or is it minus? It's minus, isn't it? Okay, e to the 5x plus c. All right. All right, let's check. Hey, that's great. All right. Oh, I guarantee you, I give this problem all the time. And yeah. Hey, you remember your rules of logarithms, right? Right. Log of AB was equal to log of A plus the log of B. And the log of A over B was equal to log of A minus log of B. And log of A to the R was equal to R times ln A, right? You remember that? If not, that's okay. Be careful on this one. Okay, I like to be tricky. So realize there might be something like this on a problem in the future, but one of the things you might do is say, why the heck did we have to use logarithms anyway? Well, a lot of you guys are biology people, and say you were looking at like brain size versus like gestation size, right? For mammals versus length of pregnancy. Well, you got to study animals that are like, I'm the size of a mouse or I'm the size of an elephant. Put those on the same axis. Best of luck to you. It's not going to work out so well. Okay, so that's why we use logarithms, is to be able to take numbers that are really far apart and put them together. Okay. So here, well, I can't integrate this piece. Okay, we can't integrate this. So when I'm picking up my u and my dv, I can integrate 4x. That's not a problem. So dv is 4x dx. U is going to be natural log 3x. Okay. Du, take the derivative, right? That's 1 over 3x times the chain, which is equal to 1 over x. Okay, just remember that natural log of 3x is equal to natural log of 3 plus natural log of x, right? What's the natural log of 3? That's a calculator thing, right? That's a number, that's a constant. So when I take that derivative, it's just 1 over x. So that's good. Got the right answer here. B is going to be, integrate this, right? That's not going to be, it's going to be 4x squared over 2, which is 2x squared. Okay. So here we go to integration by parts. We have uv and then v du. Okay, so uv, this is going to be, okay, this is going to be 2x squared times natural log of 3x, right, because that's my u, minus the integral, right, of 2x squared times 1 over x, there's a dx here, dx. Okay. So this isn't a bad integral. This is 2x squared times natural log of 3x minus integral of 2x, one of the x's cancel. All right, so this is 2x squared ln 3x, parentheses here, minus this is going to be 2x squared over 2 plus c. So we have 2x squared natural log of 3x minus x squared plus c. That would be an answer there. Okay, so we have squared ln 3x, right? Minus, I believe, x squared plus c. Let's see if we put it here. Very good. So let's go on to something a little bit different. I'm going to trust that you guys could do some. Oh, look at that. We're still going to go through and here we go. Actually, let's go back and do this one. Natural log of 13x dx from 1, 2, 3. Okay. So how do you do something like this? Integral natural log 13x dx 1, 1 to 3. Let's get rid of that. You're gone. Okay, so we're going to say let u equals natural log 13x b uv rather, is equal to dx. V is equal to x, and du is equal to 1. We know this, right? This is natural log of 13. This ln of x. Natural log of 13 is 0 when I take the derivative, right? The derivative of this is 0 because it's a constant, so this is just 1 over x. So we have uv, so this part, minus that part. So we have x ln 13x minus integral 1 over x times x dx. There's a dx here. In other words, there's a dx here. Right. So this is x ln 13x minus integral of this cancels, so this is just dx. So this is x ln 13x minus x, and we're going from 1 to 3, I believe. 1 to 3. This is the hardest part of your calculus problem now, doing this. Okay, so this is 3 natural log. What's 3 times 13? Minus 3. Sometimes I leave a little x evaluated in something there because sometimes I forget. Right, so this is going to be minus 1 times natural log of 13 is just, right, 13. So what is this going on here? We have 3 ln 39 minus 3 minus ln 13, and then minus a negative is plus 1, right? Okay, so what do we have here? We have 3 ln 39 minus natural log of 13 rather, minus 3 plus 1, that's going to be minus 2. There's probably some stuff we could simplify even more here, but I think this is the answer they're looking for. Let me show you what could happen. Okay, this is the kind of stuff they be able to put in our calc book. All right, well, the answers used to be in the back rather than just check answer. This would be 39 cubed over natural not over natural log, just over 13. Okay, minus 2. Okay, let's see here. 39 cubed is natural log 30 times 39 times 39. 13, which is natural log 39 times 39 times 3 times 13 over 13 minus 2. They cancel these out. They'd multiply this out. Delightful. And they give us that as the end. They don't want this. I'm not messing with that. So this right here. Okay. 3 natural log 13 minus natural log 39 rather. 3 natural log 39 minus natural log 13 minus 2. I'm sure that is, oh, they don't even want that. They just, jeez. Right, you guys are allowed to have a calculator, right? That's fine. Not one with an algebraic system, but there's a calculator. 3 times natural log 39 minus natural log 13. All right, minus 2. What do we have here? How many decimal places do they want? Round to 4 decimal places. Beautiful. So what do we want here? We want 6.4253. 6.4253. 6.3. All right. .4253. Okay, hopefully we'll something there. Okay. What did I mess up? Oh, I know what I messed up. No, I didn't. It's okay. Minus 3 minus 1, that is minus a negative, so that's a positive. Did I type the right thing in? I think I did. All right, what was the little error they gave me? Do not run into the final answer way. It knows I'm close. Okay, but in the interest of not doing all of this, we're gonna, yeah, that's fine. All right, this one could be a little tricky. This one's going to be a little tricky. All right, we have 5x squared square root x plus 9 dx, right? Now, let's see here. What would I like to take derivatives? Well, actually with this one, what I'd really like to do is like, well, can I just use a u substitution? So u is equal to x minus, I'm sorry, x is equal to u minus 9. So I'd be tempted to do something like this here. It's kind of like a u substitution from the later parts of the subchannel. So we might pick this out as a u, or 5 minus u squared times u to the 1/2, and to go through and do this, okay? And that would be a legitimate way of getting through this problem, okay? It might be an easier one than doing through all of this, but let's see where integration by parts would lead us. So this is, we'll save this for later. This is in the maybe pile, okay? So what am I doing here? We're going to say u is equal to, this is going to get smaller, so let's try this, okay? All right, and that's, even if I have to do like a thing in here, like the integration here, like this problem is not going to be that bad, right? So du is equal to 10x dx. V is equal to x plus 9, add 1, right? That's to the 3/2, and then we have the 2/3. If I take this derivative, right, checking to see if there's a weird chain going on here that I would have to add in. I don't see one though, so we're okay. So here we go. We have, this is 5x squared times 2/3 x plus 9 to the 3/2 minus, and then integral of 2/3 x plus 9 to the 3/2 times 10x dx. So let's go ahead and clean this up a little bit. This is 10/3. 5 times 2 is 10. Okay. X plus 9 to the 3/2 minus integral. This is 20/3. Okay, we can pull the constants out of the integral. And this is x plus 9 to the 3/2. Okay, and then still, right? So we have to do this twice, right? Now, even here, we could say u is equal to x plus 9. X would be u minus 9, and go through and do it this way, okay? We could do that. All right, let's continue. So this would be a good place to like bail out of integration by parts and try this instead. That's fair. Let's keep going with integration by parts. Like, okay, I've made my choice. I'm going down with the ship with it. Okay. So here we have 10/3 x squared x plus 9 to the 3 halves minus 20 thirds. Okay, so here's my integral, x plus 9 to the 3 halves dx. So we can think about this almost as a brand new problem. Okay, we're going to set u equal to x, du equal to dx, dv is equal to x plus 9 raised to the 3 halves. Get me the exam out of the way here. Okay, this is dv was to the 3 halves. So v is equal to x plus 9 to the 5 halves and then 2/5 here. Okay. So again, take the derivative, double check it, right guess and check kind of a thing. So this is going to be 10 thirds x squared, x plus 9 to the 3 halves minus 20 thirds. Okay, we have uv. So this is 2/5 x plus 9 to the 5 halves minus the integral 2/5, okay, x plus 9 to the 5 halves times dx. Okay, be careful about this piece right here. Yeah, I guarantee you all of us are going to forget this. Okay, so try to be good about not losing this piece. Okay, negative included. So 2/5 x plus 9 to the 5 halves, and then minus that we have to go ahead and integrate this. So it's 2/5 here. Integrating this, we have x plus 9 at 1, 7 halves, right? 2/7. See. All right, now distribute. Okay. See, I knew you guys were going to still have some fun here because they were going to allow you to do this thing. They definitely have some problems where you had to do this twice as well. Okay. What's 20 over 5? Isn't that 4? Okay. Let me not do that. Okay, so 20 over 5, that's 4. 4 times 2 is 8. We cancel the 5, so that's just a 3 here. X plus 9 to the 5 halves. Negative times negative is positive. Again, oh, look at this. We have 4 here. We have a 3, 5, and a 7 now. Okay, we cancel the 5. Oh, let's save that for another spot. So that's going to be 4 times 20, 4 times 20, times 3, times 5, times 7. And that's x plus 9 to the 7 halves. 20 thirds times a constant. That's a constant. All right? So we have 10 thirds x squared, x plus 9 to the 3 halves, minus 8 thirds x plus 9 to the 5 halves, plus nothing cancels with the 4, the 5, and the 20 cancel. So that's going to be a 4, so that'll be 16 21s. All right. Okay, let's go see. So yeah, you guys get to have as much fun as, well, maybe not quite as much, but a lot of the same fun that the engineering students get to have with having to do this thing twice. A lot of problems make you do it twice. Sorry, that's the way it is. All right. And from there, let's see. Integers are fractions for any numbers. So what do we have here? We have 10 thirds x to the squared times, let's do it this way, x plus 9 raised to the, what do we have here, 3 halves? Let's use parentheses. and then go with minus 8/3 times x plus 9 raised to the parentheses. I believe it was 5/2. All right. So that was, yeah, and we had 16/21. Okay. X plus 9 to the, not doing that, to the parentheses 7/2 plus C. Just 9 7/2. Cross my fingers here. Hey, look at that. Okay. There's no arithmetic, so I'm likely to get a better answer. All right. I think I'm going to leave it there because I think the video is long enough. All right. But in this section, I think eventually yeah, okay. I think eventually we are going to have somebody they try to trick you. Actually, I didn't see any they tried to trick you. All of these are just straight up integration by parts. So you should be good. Okay. I will not be so nice. I can't give you some you have to figure them out. There's some integration by parts, some not, but I understand. All right, I'm going to stop this video and post it, and then you guys can get started with all of this. All right, good luck.